what have I learned in the past couple of days, 3 days? What has impressed me is that we have fine-tuning problems all over the place, and especially the ones that we know best, that we test best, are in particle physics. And there, it seems that we're dealing with fine-tuning of 1 part in 100, 1 part in 1,000 of that order in current models. Everyone accepts that, nothing special. There's a big push now to build an accelerator at least 10 times more powerful than the LHC, which would get us up to 100 TeV, rest mass energy, acceleration energy. And that would open up the door to testing fine-tuning to 1 part in a million. That may or may not be found, but that's the sort of goal we can do. So in particle physics, numbers like that are not, are reasonable. People accept that. Then what about the larger scene? So we've heard two strong arguments for which have led us to multiverse type reasoning. So one of those arguments comes from the resonance in the carbon atom, which is often cited as one example of anthropic prediction, although at the time, of course, Fred Hoyle had no anthropic thoughts in mind whatsoever. But we learnt today that that's only a fine-tuning of 1 part in 1,000 of the fine structure constant, so that seems nothing special. And then the main argument that we're left with is that's considered to be experimental verification of anthropics, is Steven Weinberg's prediction that the cosmic constant should be of order unity in the usual dimensionless units today, which would imply some incredibly small value back in the past. Now, I have a couple of problems with that. One is that it turns out to be an incredibly imprecise prediction. I mean, for one thing, the upper limit was based on structure formation, and one can live with a much larger value than unity if you make the structure early enough, in principle, and make life, etc. And then there's also the question of the lower bound. And in fact, lambda could be negative. In fact, if you take string theory as it currently exists in anti-de Sitter space, it is negative, because that's a negative cosmic constant. That, in fact, would accelerate the growth of structure, which at one time was thought to be a necessity for structure formation, to understand how we came from such small fluctuations. So the conclusion would be that lambda could have a range of values from anthropic predictions, and so it's not clear that the measured value is really a prediction. So that leaves us then, however, with the one problem, major problem, that if we take the so-called natural value of the Planck moment, say, or some slightly later moment, then we come up with this 10 to the minus 120 fine-tuning needed to get a universe as large as it is. So the question is that fine-tuning, which is, larger than the ones we're used to, of 1 part in a million, 1 part in 10 to the 120, is that something that we should be worried about? I'm in two minds about that, because today, if you want to describe the universe that we see with dimensionless numbers, you can very nicely. The Planck satellite can reproduce perfectly all the data with 6 numbers. And then Martin Rees pointed out you add 3 more and you've got everything you need to even produce your observers, if you want them. The trouble is, of course, that explains our model, but it also, to avoid extreme fine-tuning, means you better not extrapolate too far back into the past, and then the numbers are not unacceptable. So what is it? Are we being very presumptuous in going from now all the way back to the Planck time to develop this immense problem with fine-tuning? Or could you imagine that something happened much more recently that would account for this apparent smallness of the vacuum density? And the one example that comes to mind is if you equate the measured value of the cosmic constant with an equivalent energy density, you find it corresponds to what would be an energy of a millivolt, okay? And you can imagine that that's a natural scale. We measure particles, the neutrino has of order such a mass, for example. You can imagine there was a late-time phase transition in the universe, for example, at temperatures of order of a millivolt that would have solved this problem for us. And this is an example of how it's dangerous to connect from now back into the distant past. Anyway, that was just a thought I had. We're constructing a huge multiverse concept on the basis of what really amounts to one severe anomaly, if you can call it that, the cosmic constant in terms of fine-tuning. So that's my thoughts. So let's just go around in order, maybe. Nick, perhaps.
So I'm not a physicist, nor primarily a philosopher. I mean, done some of both. But what I'm really interested in are these big picture questions for humanity. And obviously, cosmology is one discipline that deals with a certain class of big picture questions. If you're interested in reality, well, most reality is out there. So this cosmology is a natural discipline to get interested in. But if the goal ultimately were to discover a lot of truths about the structure of reality, to get answers to big picture questions, then one can think about a direct approach, which is what almost everybody is pursuing, which is do the science, do the philosophy of physics, do the statistics, try to actually make progress at the object level on some of these big picture questions. Or one might take the more patient and indirect approach of trying to put ourselves or future generations in a better position to find out the answers. By making sure that we have a civilization that thrives, that survives. Maybe we have cognitively enhanced scientists in 50 years or 100 years, and whatever problems are solvable but difficult for us to solve, they could probably have a greater chance at then solving. So that's really my ultimate concern, not just because this would deliver answers to questions of physics, but because it seems like a sort of a dominating value in general to ensure that all these possible future generations that could come to exist will come to exist in a good way. So why then this interest in anthropics? Well, surprisingly, it turns out that some of these big picture questions that anthropic reasoning is relevant to might have a bearing on how best to succeed with this enterprise of trying to reduce existential risk and trying to secure a long-term future. It turns out, for example, that applications like the doomsday argument, if it is correct, would have a huge bearing on how to think about our long-term future. So then it becomes very important to try to figure out whether the doomsday argument actually is sound or not. It turns out that once it starts to pull at that, it's connected to other applications of anthropic reasoning. It's connected to fundamental paradoxes in epistemology. It's connected to anthropic reasoning in cosmology. And so you need to start to think about all of these things to get clearer about some specific thing that is ultimately relevant. And there are other applications. I mentioned some in my talk. The simulation argument is one. Thinking about Fermi paradox, which might help us get a better understanding of whether we are alone in the universe or whether we will ever encounter other extraterrestrial civilizations. And if we don't, then what happens to them? Were they never there in the first place, or was there some common mode of disaster? So it turns out that there are a few of these indirect constraints that narrow down the range of coherent pictures one could have about the future and about our place in the world. And it seems that in order to have a well-founded view about what we have most reason to do, what would actually, all things considered, do the most to reduce existential risk, increase the chances that we will still be around in the long-term future and solve all of these physics problems, among all the other wonderful things we could do, one needs to think really hard about this set of big picture questions to try to figure out the kind of macro strategic landscape that we're operating in. So hence my interest in these things.
So I'd like to make 2 points. In a conference like this, I think one of the things that emerges is points of contact between physicists and philosophers, where people are coming at similar questions from very different angles. And one of the exciting things is that there's really a possibility of these different angles being productive ways of looking at the same problem. And so I'd like to just emphasize 2 things that strike me as areas where it's useful to have an interdisciplinary approach. So in particular, reflecting on the style of work that Nick did in his book on anthropic bias and a lot of the philosophical literature that's sprung out of that. There's a lot of discussions about how to think about beliefs that have an indexical component and reason about situations where you have agents who are in these sorts of scenarios where they have indexical beliefs and how they should reason in those sorts of situations. And I think there's been a lot of ingenuity in exploring the implications of those sorts of things for traditional issues in methodology. And I think the challenge is to take those discussions from the philosophical literature and see exactly how they relate to the kinds of evidential problems that scientists are facing in trying to reason in other contexts. And so I think there's interesting work in the philosophy literature, and then there's a set of questions that are related, but it's actually quite tricky to determine exactly how the relation should go. So in that kind of situation, I think the key questions are to say, well, in these thought experiments, are there assumptions made that are appropriate for the sorts of philosophical questions that people have been posing, but inappropriate for reasoning in the scientific context where you might hope that there would be an analogy? And so partly I was arguing that there are some cases where I think there are disanalogies, but I think there's a lot more work to be done there because there's interesting work on the side of philosophers considering methodology. Another thing that is more a side point is just that philosophers often don't get their hands dirty enough in terms of looking at specific cases of how reasoning goes and looking at actually grinding through how a particular case of evidential reasoning works in practice. And so I think when we look at Bayesian approaches, they're very popular in philosophy, but they're actually very computationally intensive to apply in real cases in the sciences. So I think there's sometimes a misunderstanding of why a Bayesian approach wouldn't be adopted, why it's so limited. From the physicist's point of view, it might seem unnecessarily complicated. And I think trying to address those, it would help to have some more detailed case studies and that sort of work. The second point, I think, is that there are periods in physics where I think methodological issues come to the fore, and people are not just asking object-level questions about particular theories, but asking meta-level questions about how we should go about assessing theories. And the discussion of naturalness as a heuristic and other topics that have been discussed over the last few days strike me as really focusing on the methodological level discussion of how it is we should be evaluating our theories and how we should be evaluating them, different rules for assessing them. And I think there philosophers and historians can draw on contrast classes of other fields and again perhaps have some illumination to shed on the current case by looking at past cases where similar sorts of heuristics were important and perhaps see the flaws or the potential rewards of adopting a heuristic like that. So I think because of the way that some of the discussion is going now in cosmology and fundamental physics, I think there's actually some place for historians and philosophers to enter in this kind of debate.
So I think what I presented was really what we know about physics today. I've not tried to do. I just presented physics that is accepted by anyone. I didn't know to very high energy scales, and I think it showed many things. First, it showed that in this series you have these numbers and you don't know what is the numbers. And I think we have to keep in mind. I mean, when I started to do science, I said it was really because I was amazed by things around me, and you want to understand how it works. I mean, like a kid, you want to understand how it works, and you realize that you can use mathematics. But then you build this series, and you see all these series, you have these actions, and you say you have fields, you have constants, you have structures, and no one will tell you what these structures are. You have to decide by yourself, and this is just because you have the world around you which tell you that, if you put a vector, it behaves this way, if you put a spinner, it behaves this way, and so on. If you have this symmetry, it means these things. And I think over the centuries, we have learned that there are mathematical structures which are very helpful to define, to describe many phenomena. We don't know why. It's just a fact. It's an empirical fact. And we write a series. We have an action. We extremize an action. We don't even know why we're allowed to extremize an action. And we have these things, and we accept that this is a standard way to do science. And the reason we accept that is just because each time we are looking for equations and we're trying to set up an experiment, we can control that the equation we have derived, they are in agreement with what we are saying. And I think this is a chance, because otherwise we would have no guidelines. So this is the first point. We don't know why the structures are the way they are. And I think at some stage we would like maybe philosophers or someone else to explain why this is the best structure. And then you have two ways. Either you do like Nima was trying to do, is say, well, if you look in all the possibilities and you argue with a lot of words and a lot of infinities everywhere, that the only structures are very similar to the one we have today. Or you try to take this attitude of philosophies just to trying to define which are possible words. And I think these both attitudes are very interesting, but it delimits some boundaries between the kind of physics that I've been doing when I was, at university and when I am in Institute of Astrophysics and when I discuss of the universe with you here. I think it's completely different questions I want to ask. Mm-hmm. And I think we have to keep that in mind. Where is this boundary lying? Because then at the end, well, if you do public outreach, you go and tell people how the universe is. What should you tell people? Will you go and say, because you are a cosmologist, that there is a multiverse over there? Or won't you say that the only thing we know is about our observable universe? Where do you put the boundaries on what you think is established and what is not established? And I think we are trying to push all these limits. Then what I was very interested is what you are able to do. I mean, if you look at how technical it was for me to just get like a constraint on any number, and then we get that maybe the only real problem is the cosmological constant problem. And then we develop all these arguments based on pure logic. And you have these Gedanken experiments about doomsday argument. For me, they are purely Gedanken experiments. And you see, this is a way to argue, and then you just try. Basically, at the end of the day, you get a conclusion on the way nature is without even looking at nature in some sense, because you can forget about all the details of nature. You can forget about the fact that you are nuclear physics, electromagnetic. The only problem is the cosmological constant. And for me, it's a real problem because the cosmological constant is the only parameter for which we have no microphysics. I cannot compute anything, just take that as a fact. And you see, for the other theories, I was able to look at the microphysics, to look for things, to look how they are connected, and I can't say anything. And my problem is that if you don't have any microphysics, then I think you can reach very different conclusions. So I try to put some thoughts about what it can change for the multiverse, but I can construct, for example, examples in which, the cosmological constant is a pure number, and I say I don't know, it's a kind of, it has distribution, and I can take the Weinberg argument so that, on the space I'm interested, it's pretty flat. I have this prior on the PDF. But then I can say, okay, imagine that this is just a function of n randomly distributed constants, which are all randomly distributed. Well, square root of phi 1, x1 plus x2 plus xn is not homogeneously distributed, and it could be picked outside of the domain of the anthropic domain. So if you don't know anything about the microphysics, you can always tune things so that actually you get to the answer you want. So the question I would like to ask you, for instance, is, people are saying that the multiverse predict omega lambda equal 0.7 or plus or minus something. I mean, how sure are we of these things? What are the loopholes in the argument? You try to answer to it. Right. But then I was feeling uneasy. You say, there is this dependent on sigma, on the measure, and on the anthropic domain, and either your prediction do not depend on that. So where is this number coming out from? I mean, it's like magic for me, or it depends on that. So how do we choose? And I think this is where I start to feel uneasy about this kind of reasoning. On one hand, I would like to have something that I could be able to use to explain, because I think we have to try as hard as we can to explain the structure that we are using to explain the world. We cannot just stop there. But now we are stuck there. This is the way the world is. It works like that. And I have spinors and I have S23 and this is the way it is. And then I can extrapolate as much as I want. But, mathematical extrapolation is like Amazonian forest at the power infinity, if Nima were there. So how can you help me to guide me in my construction of the next stage of physical theories? I think what I would like to know.
Do you want to briefly respond?
Well, in terms of, I'd love to be able to guide you in the next stage of development of physical theory, but I think for philosophers that's a high demand. In terms of I think there's a really basic question about what is a satisfactory sort of explanatory stopping point. And so I think you're right that it would be nice if you had somehow a deeper underlying fundamental principle that would allow you to understand a lot of the structures. But there's a real issue in terms of at what point is it unreasonable to make a further demand, and what kind of thing would you get as a further explanation that would be somehow less complicated than what you already have. With regard to the question about the cosmological constant, so I was arguing that the prediction, as it were, is very weakly related to any of the properties of the multiverse that are proposed. But there's a set of issues that I didn't even bring up, which is just that in the argument as it's usually given, you're only varying one parameter. And so if you start wondering about varying a lot of parameters at once, then I think it gets even worse, because then you are in this... So Weinberg gives an argument that the prior PDF should be uniform over the anthropic interval. He just says that the energy scales at which particle physics might be expected to change the value of the cosmological constant are so far out of that, so you'd expect it to be flat within that interval. But if you start considering a lot of different constants varying, then that assumption gets weak. And also it becomes a lot less clear how to deal with the interplay between the different constants that are varying. So I think you're right that when you try to think through the prediction in a more sophisticated way, it really becomes problematic.
Okay, so let's open this up.
From the anthropic viewpoint, there are a whole lot of different fine-tunings needed to allow life to come into existence, as Martin and others have pointed out. So now some people have the idea there'll be this fundamental theory, and if we had succeeded in fundamental theory, they would have predicted all of these constants. And those constants, so you've got your fundamental theory, you've got your effective theory, and then you've got life. And what we do know is that you have to lie in a restricted range in the effective theory in order to get life. Okay? Now, if you had a fundamental theory which predicted exactly all of the constants in the effective theory, and if that had worked, we would have had a much bigger problem, because that one over there in the fundamental side, based on SU5 or U8 or whatever and variation principles, it could have landed anywhere in this effective theory space. And why would it land in that very small subspace here, which allows life to exist? I think that would be a far bigger problem. So at that level, I actually like the multiverse as an explanatory mechanism, because if you scatter ones around, then you have a chance of finding it. And so actually, that idea of one unified theory that would produce one precise set of all those constants, I think that causes a far bigger philosophical problem for life than the multiverse.
Completely agree.
Just to comment on George's comment, that in fact it seems to me that tastes change. I remember well from the early days of string theory that they were so confident they were going to get the one theory which was absolutely unique and would explain everything. And now, I mean, 30 years on, they're saying the great virtue of string theory is that it doesn't do that, that it gives a great variety of effective theories. So, I mean, I think one should be just a little bit wary of changes of taste.
Mm-hmm. But maybe we try to put, like here, you want to go from 0 to 1, like explain everything and some environmental dependence. I mean, for me, as I far I know, each time you have a question and it's 0, 1, it's somewhere in the middle. There are things that you will be able, if you understand better the physics, you may find correlations between different parameters, and you don't need to explain some of the fine-tuning. They will just be coming from the consistency of the theory. I mean, one of the issues was, for instance, what about the dimension of space? I mean, it could be 3, 4, 5, 6, even not an integral number. Usually you don't have an answer. If you write general relativity, you can work with a manifold, whatever dimension you want. But in string theory, they have, for some mathematical consistencies, they predict what is the dimension of space. It's not free anymore. So we can think that some of this freedom will disappear when we understand better the physics, and some will remain. We don't know which one have to be remain, and I think we assume now that the cosmological constant is the one to be remain, and then we go up to these constructions.
Mm-hmm. Yeah, I mean, maybe I can come back. So if it had turned out, or if it does turn out, that there's this fundamental theory that does pinpoint down all these parameters, it's not clear that would be worse. I think it would depend on how it did it. If it were a very simple fundamental theory that surprisingly had this very precise implication, I think one could then argue that would be a satisfactory answer. A simple theory should have a higher probability, and it just turns out to be a discovery we make about how certain parts of maths work, that there is this very simple model sort of in the hierarchy of complicated mathematical models that yield these particular values. So we would be surprised maybe to find such a theory, but it might be the kind of surprise that we discover when we prove a mathematical theorem that is surprising, that like God should not have been surprised to find this if he perfectly understood all the different concepts and mathematical implications involved. So I think that such a theory, if it were found, could be quite satisfactory.
What you would be saying then, that in some sense the image of life is built into the whatever group it is. To me, that's an extraordinary concept.
Yeah, well, I'm not saying that it is, but I'm saying that if we did discover that it was built into some very simple piece of mathematics, and built in the sense not built in along with the whole multiverse, but specifically this particular kind of universe that we live in was built in some very simple Turing machine that outputted this, then that would be a surprising finding for us. It would be amazing, but if that turned out to be the way it was, then that's probably the theory we should believe in.
So there's one beautiful, I would call it proto-example of this in string theory, which is that Philip Candelis and others have shown that if you classify some vast number of Calabi-Yau manifolds by Hodge number, you find that when you get down to requiring spaces that could only contain degrees of freedom sufficient to match the standard model of particle physics, there's 3 of them are left. So simplification might be buried there in mathematical descriptions of string theory. This is just the glimmer of something that might be discovered later, but I think some are moving in that direction already.
I find myself still baffled somehow right at the beginning, and I wonder if I can just present some thoughts about it. I mean, one sort of issue which has always made great sense to me is the metaphor of the net, the fisherman casting the net. Indeed, the poster for this conference is based on that. And it seems it's a very interesting and appropriate observation to make the point that, well, you're not going to catch any fish which are too small for the mesh. Mm-hmm. And that seems a very simple, very beautiful observation, and somehow we must learn from that. But here's another thought. Well, you're not going to catch any very large fish either. You're not going to catch any sharks, because if you did, they'd eat you up, and then you wouldn't have caught them. And that seems to be a mistake. So, and sometimes I wonder whether we don't veer from the one to the other without quite realizing it. And I think the question of the very big fish, it's something like the wrong order of explanation. It's a bit like the barometer that reads the high pressure or low pressure for a storm, and you think, oh, that explains the storm. No, that seems wrong. It's the storm that explains the low pressure of the. So something like that perhaps is going on. But here's a suggestion about what might be going on in the community, especially the eternal inflation community, and it especially comes in with those who are concerned with things like Boltzmann brains. So here's one sort of question you can ask. Given that you are some sort of conscious observer, what are you likely to see? So that's one kind of question you can ask. And then perhaps the issue of Boltzmann brains becomes really rather relevant, because presumably they are conscious observers. So if most of them are, in orbit around a black hole, then most of them will see a black hole, and that's what you should expect to see. So that's one sort of question you can ask, which sounds a bit like an anthropic sort of argument. But here's another sort of question that you can ask. Given that you are whatever you are, does that introduce a bias in what you're likely to see? And I think that second question is the one that comes closer to the mesh of the net being whatever it is, and you're not going to catch any smaller fish. But if that's what's at issue, then it seems to me Boltzmann brains would never come into consideration, because unless, of course, we consider ourselves in a skeptical problem, are we, good grief, maybe we are Boltzmann brains or something like that. But if you're not going to even hold up that scenario as needing any real consideration, given that we are what we are, carbon-based life forms, perhaps it's enough that one isolates whatever is required for carbon-based life forms to exist. And perhaps one thing there is stars. Stars are required. So I'm coming back to a suggestion I made 3 years ago. Chris, you were kind enough to remark on it. In other words, find something downstream, really, from our own origins, something that screens off our contingency. Once you've got stars, there's all sorts of other contingencies that might follow from that. You might get a population of 1 billion people, or 100 billion people, or just 1 million people, but it doesn't really matter, because those sorts of contingencies just aren't relevant to possible bias, observational bias, For sure, we're only going to see a region of the universe which is hospitable to stars, but it doesn't really matter how many people are located in that region of the universe. So that's my thought, and that would seem to suggest that there's something wrong with the reference class idea if the reference class is going to somehow quantify over numbers of observers. But perhaps that's not what, Nick, you have in mind with the reference class. I would have thought it leaves the Bayesian approach more or less intact. So just, can you comment on that?
Well, regarding the Boltzmann brains, if one consider the proposal to sort of rule them out by fiat, or just stipulate that although they might be there, we should just assume we're not one of them and then proceed, it has a kind of unsatisfactory ad hoc feeling to it, at least from my point of view. You could consider a range of cases from pure Boltzmann brains that arise out of gas clouds from random encounters of atoms to less and less Boltzmann brainish things, but maybe it's not just a brain that materializes, but with a whole little local environment or an ecosystem, or something that starts with a planet, but then a lot of sort of quantum fluctuations occur to make life happen. And there seems to be a continuum there, and it seems unsatisfactory to draw a line at one particular point and say we should just pretend as if the other part of the continuum didn't exist. Particularly since we have a way of reasoning about these things that don't require that. That also has some implication that bites, namely that we could be Boltzmann brains, but most Boltzmann brains would have very chaotic perceptual states. The fact that our perceptual states are not very chaotic then gives us some evidence against those theories that say that Boltzmann brains dominate the picture. So it's nice in the sense that it provides one way to link this class of theories to something that we can test, and we can then use our observation to narrow down the space of possibilities.
Could I pose a dichotomy? One can ask the question, what should a generalized intelligence observe? Another question, how do we compensate for possible selection bias? Would you agree that the simulation argument is entirely directed to the former and not the second?
So I'm not sure
The former was the question, what should an intelligent being expect to observe, or expect, as it were, to find themselves, where are they going to find themselves located? The other is, how do we correct for observation bias? Would you agree that you are addressing the former and not the latter with the issue of simulation?
Not necessarily. So I think the simulation argument makes only very weak demands on the reference class, in that even if you restrict the reference class to only include people very much like us, human-like observers, maybe living around the early parts of the 21st century, that it could still go through. You don't have to assume that post-humans are in our reference class, or apes, or aliens. So in a sense, it is on a stronger footing than some of the other applications of anthropic reasoning. And it doesn't necessarily imply that the randomly selected observer from all observers in the universe would be in a simulation. Maybe it's mostly people like us who are simulated and posthumans are not simulated. That would be a consistent possibility that would be compatible with this trichotomy that the simulation argument tries to establish.
If I could comment, I mean, I have a worry that there's an ambiguity that's, I think, very similar to the one you're worried about in these sorts of scenarios, where people sometimes motivate the Boltzmann brain scenario by saying, well, in an infinite universe, the probability of the likelihood of somebody having exactly your data is going to be 1. But then there's an ambiguity in what they mean by your data, because in some cases it is given this very solipsistic, skeptical kind of gloss where you say your data is just the whatever mental state you happen to be in at the moment, and it could be completely non-veridical, and we'll consider that as being somebody with exactly your data. There's a different way of reading it, which would be, and now that I've heard Jean-Philippe's talk, I have a lot more data. That would be all my data about everything in my Hubble volume. That would specify an enormous amount about about the universe I live in. You might still argue that the probability of somebody with that data my data in the factive sense, namely that I have correct beliefs or largely correct beliefs about the the universe I live in, you might still say that that is close to 1 in an infinite universe. But in that case, then it's not clear to me why I should worry about whether I'm me or the other person with the identical data, because in terms of the inferences I'm going to make from that data with regards to physical laws, it should be exactly the same. And so you can't solve the problem of induction, so maybe that Hubble volume is embedded in a universe with slightly different physical laws that will be revealed as my doppelganger goes off into the future, and I'll see some different physics. But we can't expect an inductive methodology to solve that problem. But I think that has a very different feel to it than the kind of skeptical Boltzmann brain scenario. So I think that those two things get mixed together in a way that's not particularly helpful.
Maybe I think it might require a particular heroic form of epistemological externalism to suppose that we have some direct epistemic access to the entire observable universe. If you consider various situations in which, say, our measurement apparatus malfunctions, and so when we think we see a remote star, it's actually just a speck on the telescope or something like that. Those, like, if we knew that most telescopes had the speck there, we should think that the thing we're seeing is probably not the remote star. And so even if you thought that sort of ordinary objects in our immediate environment were something we had direct epistemic access to, you could still imagine these kind of fluctuations just being slightly larger. So not just a brain in a vacuum, but a brain along with a room. But I think it would be a bold assumption to just postulate that we can't be wrong about things that are in.
All I'm claiming is that there's separate issues. There's an issue about skepticism and a response to skepticism, and then there's an issue about what possibilities arise in an infinite universe for having duplicates with the same data. And so if you want to be a skeptic, that's fine as well. But I think it's a separate issue than what arises due to the infinity of the universe.
I wanted to say two things. One, in all this context where people speak about anthropics, like this meeting, the mantra repeats itself that in an infinite universe you have everything and copies of everything. I think that is totally wrong from the point of view of mathematics. I don't know whether in physics there is some higher wisdom, but of course, if you have an infinite set in the mathematical sense of infinity, rather let it be countable or uncountable infinity, you can have lots of infinite sets where not all the possibilities are realized. To begin with, think of the most trivial cases, like the set of natural numbers. Of course, the set of even numbers is, of course, an infinite set. But you have to begin with all the odd numbers that are not realized there. And the same thing, you can take the set of real numbers, for example, in a line of the real plane, and all the other points are not in that sense. So it needs some supplementary argument to say that in an infinite set everything happens and there are copies of everything. And this type of Tegmark-like pseudo-arguments that because in an infinite set everything happens, that's a principle of his creation, that is not a standard principle of mathematics, then there are infinite copies of me in infinite worlds and so on. And the second question is that also, well, when we speak about the constants and the combinations of constants necessary for life to arise, that is a very complicated question in the following sense. Physics and chemistry are universal sciences. We think that the atoms on Earth are the same as the atoms everywhere. But biology is a provincial science. The biology we know is the biology of life as on the surface of Earth. And this life had characteristics which come from inheritance from a common ancestor who possibly by random reasons got certain characteristics. And And from that point of view, we do not know. Usually, anthropic authors speak about things that have nothing to do with humans, nothing to do with observers, nothing to do with consciousness, but have only to do either with carbon atoms or with galaxies. And how the constants have to be in order for galaxies to build or in order for carbon atoms to build. But if there is life somewhere else, as probably it is, perhaps it is not based on carbon. Perhaps it is not even based on the electromagnetic force in the type of chemistry. Perhaps it is based on some different fundamental force and so on. So we do not have any idea of how life anywhere is going to be. And I think everything would be clearer if instead of talking about anthropic considerations, we talked about something like carbon considerations, because then we would know very well what we were talking about. Because of course, I think that I've spoken enough. Thank you.
Well, I mean, on the first thing there, so it is true, it requires some additional assumption other than infinity itself. For example, the assumption that there are these stochastic phenomena that are independent of one another and that there exist throughout this infinite thing. It's like infinitely many planets where random things happen. So the having all possibilities realized, it's in the same sense as if you have a coin toss of a fair coin and you keep flipping it infinitely many times, then any finite sequence that you specify, you will with probability 1 find embedded in this infinite sequence. In fact, you will find it embedded infinitely many times. And instead of having this in time, you could have this in space. You have infinitely many places where random things can happen, maybe with astronomically small probabilities for any reasonably sized volume. But if there are enough of these volumes, then even the astronomically improbable will rise to probability 1 when you add them all up, as you can if they are independent. I can say something about the second, but maybe you want to...
No, well, I think I agree. It should be the carbonic principle, but it's not trendy today to speak about these kind of things.
So there, just as a joke, I've heard it referred to as the rutabaga principle, with the idea that wherever there are humans, there are also rutabagas. So
yeah. So I mean, I actually have a different view on that. I don't think it has anything to do with carbon. Per se, whether we are implemented on silicon or carbon or something else, it wouldn't change the fundamental methodology. It's the observation selection effect. The preconditions for having something that is making the observation. Now, there are many preconditions. So, like, as far as we know, maybe you need a planet, maybe you need oceans, maybe you need a whole host of things. It would be wrong to pick out any one of those, carbon. It's whatever it's necessary, but the criterion for whether they are necessary is that there is an observer or an observation taking place at the end of it.
No, that if it is, perhaps you could do similar arguments with other forms of life, but actually, if you look at the concrete arguments that have been proposed, once I was discussing this with Vilenki, for example, for a long time, and I was writing down everything he said, and everything he said had to do either with galaxies or with carbon atoms. And the only physicist I know who made something who had anything to do with consciousness was Wheeler, with his so-called, at a certain moment only, his so-called participatory anthropic principle, where a consciousness was needed in order to bring the wave function to collapse. And that was a real use for consciousness. But in the rest of the anthropic arguments and considerations, the consciousness play no role. Of course, you can say if there were no observers, there would be no science and so on. Of course, but you could also say if there were no speakers, there would be no science, and we would not be here speaking about the matter. But the question of which values the fundamental constants of physics have to do in order for galaxies to build or for heavy atoms to build has directly nothing to do with consciousness and nothing to do with observership. Of course, perhaps it leads to observers, or perhaps it leads not. The universe is very old, and perhaps for billions of years there were no observers at all, or perhaps there were, I don't know. But it is not something implied in the fact that the fundamental constants have certain values that consciousness or observership or speakership or whatever are going to arise.
This is a point that Simon emphasized a few minutes ago, and I mentioned in my talk as well. I mean, I think the main reason for doing calculations of focusing on proxies such as galaxies is because you can actually try to do the calculations. I think there's an assumption that will screen off other details relevant to the development of life in terms of the physics you're looking at. If you're looking at the physics of gravity, presumably details about the chemical environment on the surface of the planet Earth are going to be screened off just by the existence of the solar system and whatever gravitational effects are relevant to that. So there's an assumption there which might be false, but I think it's also pragmatically motivated just by the need to be able to actually perform a calculation. Otherwise, you don't really have a way of handling the selection effects when you're looking at the physics. So the proxies are often quite far removed from details about human existence, but I think there's good motivations for that.
I would make the argument, and so would many scientists, that reasoning, the thing about anthropic reasoning is it's a class of reasoning from a constraint, as you mentioned several times. It's, you mentioned the word compatible with. But of course, what an experimentalist would always want to know is, yes, but is that an explanation? Now, I know that's very simple, but you're immediately brought into the territory of, well, what constitutes an explanation from a scientist's point of view? What is scientific explanation? And I remember when the whole business of anthropic reasoning first arose in cosmology, I really thought a whole sort of generation of books would arise written by philosophers of science on new methodologies in science, but it didn't really happen. And that brings me back to the point you made about there's a sort of a hole there, because I would even put it almost as a challenge: as can reasoning from a constraint ever constitute an explanation in the normal sense of what we mean by explanation? But I think a nice tie-in there with this sort of history and philosophy of science that you mentioned would be, if you look through the history of science, I'm sure you will find absolutely dozens of examples where anthropic reasoning is used, but as a no-go theorem. When there's a fork in the road, we can always bring it as a very powerful constraint, particularly in biology and chemistry, of course. But I can't think, and maybe you know of examples of where it's used in any other way, in a deeper way, as an explanation that things have to be so, etc., etc.
So there's one way of going as employing anthropic reasoning as an explanation, which is close to the fishing example that Eddington used, and that's, I think, closer to the way Bob Dickey originally used anthropic reasoning. So it was, in effect, explaining away a coincidence that Dirac had noticed, a large number of coincidences. And Dickey argued that there's, in fact, a selection effect that's relevant to our time of observation that undercuts the evidential value of the coincidence that Dirac had tried to use in favor of the theory that the gravitational constant varies with time. Dickey said these coincidences are going to be an effect of the fact that we're observing at the particular time we're observing, to simplify a discussion. But there's a kind of explaining away or undercutting the evidential value of some claim that often, when you think of anthropic explanation as a selection effect, that often is used as a kind of explanation. But I think so there's another aspect. There are some discussions in philosophy of science about whether you could think of a more teleological notion of explanation in relation to anthropic explanation. I think that's a very different kind of theme. The theme that I've been thinking mostly about is the question of how to use evidence, how do you take into account selection effects that were important in gathering evidence and ensure that you take account of those appropriately so that you don't make untoward conclusions. You could go the other direction and say maybe there's teleological explanations, and that's some of the early anthropic literature in the sciences went that direction. And there has been some exploration of that in philosophy, but as you say, not a lot.
Is a Dickey example not really an argument from constraint? It's just sort of a very very, shall we say, convoluted version of it, but it's really from constraint, really, isn't it?
Well, depending on what you mean by arguing from constraint, I just take it as observing that there's a selection effect means that it's just like in the Eddington case. You have to recognize the size of the gaps in your fish net, and that will have implications about the size of fish that you catch. Similarly, Dickie was saying, because of what times we could possibly exist, there will be constraints on the large numbers that Dirac had focused on. And I don't remember exactly what they are at the moment, but there are these large number coincidences, which he thought of as favoring a particular theory. And Dickie said, well, no, that's just a consequence of when we're around to make these observations. And I'm sorry that I don't remember the details, but I think that's the form of the argument. I think.
Yeah, but it's different from the new way of using the entropy.
Yeah, no, and
because I would not call that an entropic principle. It's just a consistency thing that the whole physics is consistent, and observers, they come through some physical and chemistry process which has time scales, and these time scales they just also depend on the things which have been on these numbers. So it's basically like you are looping, and this is a back reaction of the fact that you want to be self-consistent. It has nothing to see with the kind of entropic principles that has been used to argue for the value of the cosmological constant.
I think it would probably count. As a very simple. You only need a very weak entropic because you don't have to bring in probabilities in this case if the observers really only exist in this interval.
Exactly.
So it's a trivial case, but still I think it would be an instance where an observation selection effect filters out of all these different times. There's only one narrow slice of times that are actually possible to observe. So I think that, and it seems like an explanation to me. If initially there's something really puzzling and mysterious going on, and then somebody tells you something, and you say, that's what's going on. Now I see. That thing was probably an explanation.
I did have a small comment in relation to this recent exchange, namely that it echoes a comment I wanted to make about George's comment. George felt that having a fundamental theory suitably entailing anthropic facts was more curious than having the multiverse, he said, construed as something like an effective theory. And I just noticed that in connection with both the fish and with the Dirac-Dickie, we're entirely assured that fish of smaller and larger sizes exist. And in the Dickie case, that there were times before which there were observers or the preconditions of the observation that give the straightforward physicalistic causal explanation of the numerical coincidence. So I'm entirely with Dickie and entirely with Eddington about the fish, but I'm not quite with the great George about the multiverse being better than the envisaged anthropic facts deduced straightforwardly from some given fundamental theory. It seemed to me, this is rather like Joe's cognitive modesty in his opening remarks about how far do we want to push the quest for explanation. The natural thing to say, probably at any stage in the history of science, certainly now, is that our theories aren't quite right. And to have wrapped up in a theory that we in fact believe effective, these wonderfully detailed explanations of a great deal, including anthropic facts, is arguably a good resting place. And it certainly, on the face of it, doesn't yet require the equal reality of the other pockets or other vacua, etc. So, this is my comment, linking the recent with what George said.
Well, yes, I think that the fundamentals are quite simple, which is which theories should you assign more probability to? Well, you look at their prior probability. Basically, simpler theories have a higher prior probability. Now, a theory could be simple because it's a multiverse theory that's not fine-tuned in itself, or a theory could be simple because it's a few specific postulates that happen to imply something. So that's one factor, the simplicity of the theory, and then you look at what conditional probability does that theory give to our observations, taking observation selection effects into account. So if you have a multiverse theory that's simple and a single universe theory that's simple, and if they were both successful in giving a high conditional probability to our observations, then both would be favored by our evidence.
I've got to disagree that a multiverse theory could be simple. I mean,
well, I didn't say that it could, but if it were, I mean, that's an additional question.
Right,
I agree
yes,
with that.
yeah.
Yeah.
infinite number of free parameters.
It suddenly occurred to me, I've been worried about Boltzmann brains and all this business about, in an infinite universe, everything will occur. Isn't this actually utter despair then? Because then we would find ourselves apparently with all different theories about the universe and absolutely hopes. Now, it seems to me that a really key thing, for me, the great story of the whole of cosmology, the whole of science, everything, is it's one fantastic coherent narrative that we get out of it. It's what I call a time capsule. The whole universe, everything we can look at, seems to conspire together to bring one incredible story. I mean, there's a line in Shakespeare's Midsummer Night's Dream, it grows to a thing of great consistency. And how the hell does that happen? And is what I want to know. And if everything can, in a random universe, can happen, I just don't feel that random things can ever produce such a fabulous story. That's just my feeling. And where do we go from this despair of everything is there to what we're actually talking about and these fabulous things that we've been hearing about?
Well, I mean,
it's 3 years ago when there was this meeting for the birthday of George. I don't remember, but some of you were there. I told this story about Auguste Blanqui, who wrote this marvelous text, in French it's L'éternité par les astres, eternity by the stars. And he's exactly making this kind of argument. So he's a communist, he's in jail after the Commune de Paris. And basically he says, well, if space is infinite, like there is a place somewhere in the universe when this commune has really worked out, and I mean the word he has managed to realize he's free and everything. So he goes on and he explains that he says if space is infinite, just I ask space to exhaust all probabilities, and it will come to copy. And it's a very beautiful text, a lot of poetry, but it's based on the science that were known in the 19th century. And at the end, the last chapter, he just say, okay, then I cannot accept that. And the guy was a communist, he was believing in progress. And he say, if you have this, you don't have progress. So he just disregards this multiverse explanation. But you see, we can tell this kind of stories, but well, we can say the contrary also. This is where I'm a little bit puzzled in the conclusion that we reach out of this. And sometimes it helps. I mean, when we were talking about this large number coincidence, it just helps us tell when this is a coincidence and where you have an explanation which is behind. And I think this is then it's a useful use of this kind of argument. And sometimes it just, as you say, you can say that and you can say something else. I mean,
but you got to count like how frequent these Boltzmann brain observers are compared to the normal ones. So under sort of the conditions we would like intuitively imagine the universe to have, like this standard Big Bang cosmology, we can even assume it's finite but ridiculously large to avoid having to introduce complicated mathematics of infinity, but still so large that all possible observations of human size would be made. The ordinary evolved observers would outnumber these Boltzmann brains by ridiculous numbers of orders of magnitude. So although they would be there, the key fact to focus on is that almost no observers, particularly almost none of the observers with your experiences, would be these Boltzmann brain. Almost all of them would have evolved on planets or arisen through their normal causal mechanisms. And that would give, I mean, I would buy into this kind of filter criterion that every scientific theory must imply an optimistic view about. I mean, did this guy believe
no. I wouldn't say that. That was the way.
Right.
I mean, I think it was very nice because, as far as I know, it was on the early, discussion about these ideas of multiverse. You have 60 chemical elements. You can take all combinations. If the universe is infinite, then you need to have copies. And I think it's great. And then, of course, you want to know whether it makes sense or not. And you see that the argument you are using is no more a scientific argument. And you can believe that, or you can believe the contrary. This is your choice. And this is where I feel a little bit uneasy. I mean, sometimes I have seen physical theories. I can say, there is this explanation of this one, and I can just think very hard and come up with an experiment to say which one is the correct one. And then there is a probabilistic explanation. And for me, a probabilistic explanation is just a partial explanation. I mean, you can have 0.99999 probability that this is the correct value, but you still have, non-zero probability that it's not the case. And because we just observe a small patch of the universe, I don't know what to conclude, that would be, that I can go to people and tell this is the way the nature is. And I feel a bit uneasy about that. Even though I understand what's behind the arguments and how you use it, I still feel uneasy about that.
Well, perhaps this is where the philosophers enter the dialogue, and eventually we will all be one happy family, I hope, but perhaps not today.
No, we are happy, whatever happens.
Anyway, I think time is over. I'd like to thank the speakers for really having produced magnificent contributions, and the audience for bearing with us. So thank you all for coming.